basically. So the bulk of titanium that we produce in the world goes into paint. All right, it also goes into toothpaste and a few other things. Okay, not that it makes your teeth whiter; it's just an abrasive. And it's non-toxic. Okay, as far as that goes. Whereas lead is toxic. That's why they got rid of lead-based paint. In any case, there's not huge amounts of titanium made. We talk about it all the time because we couldn't build. I was somewhere earlier this week, and a guy had on his computer screen, the screensaver was the SR-71 Blackbird, okay, all titanium skin, and couldn't have built that plane without titanium, okay. Aluminum would have overaged and fallen apart within hours, okay. Titanium is a higher melting point, lightweight, high strength, excellent corrosion resistance. One of the big uses of titanium is not probably the bigger use than aerospace for titanium, or at least on a par, is corrosion resistance in heat exchangers, chemical plants, whatever. A little bit's used in medical implants because it has excellent corrosion resistance. In any case, I'm going to show you the different alloys, but we divide titanium into alpha stabilizers and beta stabilizers, and I mentioned to you before that titanium has this interesting property that it changes crystal structures, just like steel. Steel goes from body center cubic at low temperatures to face center cubic at high temperatures. Titanium, on the other hand, goes from hexagonal close packed to beta BCC at higher temperatures. And this is just sort of a schematic of a alpha stabilizer. If the alloying element increases the melting point, or not melting point, but the solubility of alpha, then it's an alpha stabilizer, and if it decreases, if it went that way, it's a beta stabilizer. And so, not too hard to see that, okay? So the alpha stabilizers are aluminum. Gee, look at the whole list, okay? Oxygen, nitrogen, and carbon down here. And then there's hydrogen, actually, is a beta stabilizer. Hydrogen is not anywhere near the problem in titanium that it is in steel. It's more like the problem in aluminum, okay? A little bit worse than aluminum, but not much. Substitutional alloying, boy, there's lots of things you can throw in there, okay? And then the ones where basically the line's sort of horizontal are tin and zirconium, so far as that goes. Not a lot, I mean, with steels, we've used most of the periodic table. With titanium, we have not. And in fact, if I show you a list of titanium alloys, common alloys, with steel, I have to go on for pages and pages. With titanium, it doesn't even take a full page in the handbook to come up with the common alloys. There are many, many other alloys, but they're sort of real niche alloys. For corrosion resistance, the common grades are 1, 2, 3, 4, which are basically just pure titanium with different amounts of oxygen. Oxygen is to titanium as carbon is to steel. It's an interstitial that strengthens the titanium. So we look at it later, we'll probably find grade 4 has 50% higher strength than grade 1. Okay, grade 1 is very pure titanium. We're usually using grade 2 or grade 4. Oxygen does lower the toughness of the titanium, but it increases the strength, just like carbon does to steel or iron. We have these grades that have some palladium in it. Why would you put palladium? I mean, palladium is a precious metal like platinum. It has a price similar to platinum. Anybody know why we put palladium in titanium? In very, very caustic solutions like pH 10 or greater, you improve the crevice corrosion resistance. There are only a few situations where titanium will corrode, but at very high pH in crevice corrosion. And if we look at a periodic table, we have palladium here. We also have nickel right here. And you look here and you see we have palladium. They also have higher amounts of nickel, and that's grade 12. So they're trying to save some money by using nickel, which is not quite as good, but it's almost as good. I have never seen a titanium palladium alloy. They're in the literature, but I think since the price of palladium's gone up by about a factor of 50 over the last 40 years. I think we don't use a whole lot of palladium. We try to improve the design or whatever, or go to another material like tantalum or something. You can't just be making big structural pressure vessels and stuff out of a palladium, even if it is only 0.1% or 0.25%. 0.25% of a $1,600 an ounce material is not a good thing for structural materials. But they're there, okay? Then you come down here. Here's a plate material that has, well, let me go down here. Titanium 6 aluminum 4 vanadium. This is the workhorse alloy for titanium in the world. Yeah, you use a lot of CP, what we call chemically pure titanium alloys 1, 2, 3, 4. But in terms of all your forgings you're going to put in aircraft, your medical things, people are using 6-4. Invented about 1945 or 46 over here at Watertown Arsenal. If you've ever shopped at the Arsenal Mall, that's where they invented titanium 6 aluminum 4 vanadium. It's an alpha beta alloy, it's 2 phases, easy to weld, use it for everything. Here's a pacemaker can. Okay, I'll pass it around. This is a 35-year-old pacemaker can, but they're smaller now. But they still make them out of titanium, and it's got a gas tungsten arc weld, beautiful weld. This actually is a titanium 6 aluminum vanadium 2-inch thick weld made by electroslag technology. This one was made at Oregon Graduate Center. The first one ever made out of, so far as I know, outside of either the Soviet Union or France, was made in the room right next door to us by one of my students about 35 years ago. But then the Navy classified it. This was in the 1970s. First research project I ever had as a young assistant professor was to do submerged arc welding of titanium. Here's some of those welds that we made on 6 aluminum 4 vanadium, and those are submerged arc welds. Why were we making these welds on titanium? This was the 1970s, and titanium would make the best submarine, much better than any of the steels, much better than aluminum. And so the U.S. Navy was working on heavy section titanium in the 1970s, which is when I started as a young faculty member. I knew from my old house tutor that the Navy was interested in titanium, and they had some research money, and the guy at the Navy was a graduate of this department, and it was giving out the money. And so I got my first contract to weld heavy section titanium, which is why we made the first electroslag welds about 1980. But the interesting thing about that type of stuff is the Soviets were doing it too at the same time. And there was a guy in the Soviet Union, he's passed away now, named Gurevich. See, there's his name right there. Okay? It is, that's Gurevich. Anyway, this is the metallurgy of titanium alloys or something like that. I can ask Professor Sadoway, he can read Ukrainian. Gurevich, and here's someone making a gas tungsten arc weld, and here's the book, all in Cyrillic. Here's the U.S. Air Force translation, about 1980 or so, of that book, okay? Metallurgy and Technology of Welding Titanium, I guess that's the title. And so the Air Force translated it because Gurevich knew more about welding heavy section titanium than anyone in the world. But interestingly, and so this is 1977 and 76, and I'm reading Gurevich's papers back from the early 70s. And I didn't pay any attention to it at the time because it was just a few years difference. And there were a few years delay anyway in translating of these things. But basically about 1974 or 1975, Gurevich quit publishing. He just stopped publishing any of his basic science of titanium. And then, but I started working on the Navy. U.S. Navy was interested in heavy section titanium for submarine hulls, and they had some problems. Okay, it was expensive. But anybody know what happened in 1980? You ever heard of the Alpha Sub? You ever read or watched the movie The Hunt for Red October? And they had Alpha Subs in there. Those were the titanium attack submarines. I was coming back from Europe reading on an airplane, reading the International Herald Tribune, and here's an article about the Soviet Union has just deployed the Alpha Subs, all titanium subs, years ahead of the United States. We have yet to this day ever built a titanium sub, okay? Congress hit the ceiling, okay, because the Soviets had leapfrogged us again. When was the first time they leapfrogged us? Sputnik, okay? And they've leapfrogged us a number of times in a number of areas, but this was a huge thing. Titanium subs could dive deeper than the collapse depth of our depth charges, okay? They could go faster underwater than our destroyers could go on the surface, okay? So we had no defense against the Alpha Sub, except the Alpha Subs were all mothballed 2 years later for two reasons. One is they tended to develop fatigue cracks, okay? And they would make a lot of noise because these cracks would start rubbing inside. You could hear them. You didn't have to put on really good headphones to do the sonar to find the talent. They may be able to go faster, but you could fly a helicopter up there, and helicopters can go faster, and they could drop a sonar thing in the ocean. And you didn't have to be very fancy because they were noisy, okay? That was good, but the even better thing is I remember going to a meeting and they said, how did the Soviets solve the creep-fatigue interaction? Because it turns out titanium will creep and fatigue at room temperature or below. And what's the temperature of the ocean? It's sort of room temperature or below, okay? And I, at the time, the guys in the Navy had a big group doing development of titanium, and I was being funded by the Office of Naval Research, and so we were talking, and they said, how they solved the creep-fatigue interaction. The U.S. Naval Research Lab had studied the creep and fatigue behavior at room temperature of titanium. If you have it under a big compressive stress, it would fatigue very readily. That's what they call the creep-fatigue interaction. I said, I don't know. Well, it turns out we learned in 1982 that they hadn't solved it, okay? They just built the submarines, okay? And they ended up with 3 or 4 subs that they could park, and I guess they're a nice museum. Okay, we'll talk some more about titanium tomorrow.